Great. So welcome everybody back to our seminar. It's a great pleasure to have today Wojtek Samotij from Tel Aviv, and he will talk about stability of large cuts in random graphs. Please, Wojtek. Yes, and as
Thanks.
usual, if you have questions, please unmute and ask Wojtek directly because I don't think it's convenient to see chat. Yeah.
Right, please, don't be shy because otherwise I might just miss the notification from the chat. Thank you, Benny. Thanks for coming. So today I'll speak about the joint work with Ilay Hoshen, who's my PhD student here in Tel Aviv University, and Maksim Zhukovskii from the University of Sheffield. And the title is Stability of Large Cuts in Random Graphs. Okay, so let's start with some basic definitions. Throughout this talk, a cut in a graph will be the set of edges that crosses some partition of the vertex set of the graph into two parts. And our work actually deals with the more general scenario where you partition into some fixed number R of parts. It could be greater than two, and then you look at the edges crossing the partition. But I just want to focus on the most basic case of the regular cuts, so partitions into two sets. And as you all know, a maximum cut, sometimes called max cut, is a cut with largest cardinality. So we want to split the vertices of the graph into two parts and maximize the number of edges going across. And it will be convenient to use the following notation. So by B of G, we will just denote the largest number of edges that crosses some partition of VG into two parts. And max cut of G will be the set of those partitions that achieve this maximum. And kind of the focus in the talk will be more on the family of cuts that achieve the maximum rather than the value of the maximum that I will discuss only briefly. And one of the basic facts that probably every course in graph theory proves towards the beginning is that every graph G contains a cut which contains at least half of the edges, and kind of two easy ways to see it, or partition the vertex set randomly into two parts and you expect to see exactly half of the edges because every edge has probability a half to cross, or you just fix a largest cut, and then you notice that every vertex must have at least as many neighbors on its opposite side, on the opposite side and on its own side, because otherwise you would move it and gain in the number of edges going across. So this bound holds for every graph. However, the following decision problem is, does a graph G contain a cut with at least k edges is already a computationally difficult problem. It's actually NP complete. And so we just won't be able to determine, given a graph G, easily with the value of the max cut. And this motivates the study perhaps of the average case scenario. So instead of looking at the worst case, we'll just study the value of the cut or the family of cuts in a graph drawn randomly from some distribution. And in this talk, I'll speak about the binomial random graph GNP. So n vertices, edges appear with probability P, and here we'll deal with the very large range of P. So P not necessarily constant will be able to go down to almost 1 over n, so to the regime where the graph has just slightly more edges than vertices. And we'll be asking the two questions: what can we say about the size of the largest cut, and what can we say about the family of largest cuts in GNP for a typical sample from GNP? And let me start with the first question. What do we know about the typical largest size of a cut in GNP? And it turns out that this is already not a very easy problem. Actually, it's quite difficult. So if you just want to determine the first order term, then it's quite easy to see that the first order term is you expect roughly half the edges to cross a max cut in GNP, but already the second order term, I'll indicate that the order of magnitude is square root of n cubed p. However, to determine the constant which is hidden here in this theta is already a very difficult problem. So this constant is predicted by the so-called spin glass model in statistical physics. And it was in the setting of random graphs, the value of this constant was determined only fairly recently in a work of Denbo, Montanari, and Sen. So this is, I don't remember the value of this constant, and it comes from the so-called Sherrington-Kirkpatrick model, where you take Kn, and for every edge you put there an independent Gaussian, and you're looking also at some kind of maximal value, partition the vertices into two parts, and you look at the maximum value of kind of the difference of the sums of edges that cross minus the sum of edges that stay inside. Now, but to see that this is the correct order of magnitude, kind of this is already fairly simple. So for the upper bound, we will just take a union bound over all cuts. So we have at most 2 to the n cuts. And then the probability that, so of course, this is roughly the expected number of edges an upper bound on the expected number of edges crossing a cut. And from standard tail bounds for binomial distribution, the probability that a binomial random variable exceeds its expectation by some additive constant t is exponentially small in t squared divided by the expectation, at least for t of order up to the expectation. And if we want this expression to be small, then we need at least n in the exponent, which means that t squared has to be this n times n squared p, and this gives rise naturally to this square root of n cubed p as the best thing that we can prove using a union bound. So we'll get some explicit constant, which is not the constant that is the truth. And now, at least to see that this is the right order of magnitude, one can give the following easy argument. We're going to construct a large cut in GNP using the following greedy process. So we'll expose edges kind of vertex by vertex and greedily build a large cut one by one. So suppose we have already partitioned the first k vertices, trying to maximize the number of edges going between A1 and A2. And here comes the k plus first vertex, and we expose its edges going to the first k vertices. So these 2 degrees now are also binomial random variables, and kind of from standard approximations of binomial by normal distribution, one can see that the typical value of the difference of these 2 binomials will be at least equal to the standard deviation. And the standard deviation is square root of the size here, square root of k times p times 1 minus p. So kp1 minus p is the variance. So square root of that is the order of the standard deviation. And the difference between these degrees will be, say, at least this quantity with probability, which is an absolute constant greater than 0. So we expect that, say, 1% of the vertices will gain something in the difference between the number of edges that go here and go here. So of course, if this vertex has more edges that go here, we're going to put it on the side of A2 and vice versa. And in the end, we'll gain some constant fraction of this sum times square root of p. And the sum of square roots is of order n to 3/2 times square root of p. Will get some small constant times this. And this will get with high probability, because every vertex has constant probability to give us this gain. Of course, between the vertices, these events are independent. So now we have n independent random variables with constant probability. So with very high probability, some say 1% of n of them will get us this, so we'll get 1% of the sum, more or less. So was this more or less clear? So this, of course, I mean, there's better ways to analyze it to improve this constant, but kind of the bottom line is that using this greedy plus union bound, we won't be able to match the constants, and to find the right constant, this really requires a lot of work. Now, actually, I'll speak mostly about the family of cuts. And here's an interesting fact, or very interesting theorem proved by Brightwell, Panagiotou, and Steiger. 2012. They proved that when P is greater than 1 over n, so the graph is not very, very sparse, and at most a half, the following is true for a typical sample of G and P. If we look at any two cuts that achieve the maximum, then their distance is not greater than square root of n over p. So with our assumption on p, square root of n over p is already little o of n. So what is the distance between the two cuts? This is the minimum number of vertices we need to move to get from pi 1 to pi 2. So this will
Can I ask
be,
a question?
of course.
Why is it obvious that you have two like, why is it true that you can find with decent probability, you can find two cuts even?
So actually, this is a very, very good question. So this is just an upper bound. So this theorem says that maybe there's only a unique cut, but if there's more than one cut, then with high probability, any two cuts are pretty close. So you can move between, so take any two max cuts and you can move from one to the other by moving order square root of n over p vertices. So of course, if the cut is unique, then the same is true because you don't have to move any vertices.
So probably you want to write smaller than omega.
No, I'd say, so here the probability that it's larger than omega times square root of n over p is at most a constant over omega. So then you just take omega, which slowly goes to infinity, and this shows that with probability at most 1 over omega, you'll have two cuts that are distant. So it's probability 1 minus constant over omega, any two cuts are close.
Okay, yeah, thank you.
Yeah, sorry, but maybe this is not the most intuitive way to kind of to read it, but this is the shortest way perhaps to write it. And so they asked, in the paper, they asked the following question: can we prove something slightly stronger than that? And they hypothesized that actually there exists kind of a backbone which is common to all max cuts, which means two sets, S1 and S2, which both have almost n over 2 vertices, such that for every cut A1, A2, S1 sits inside A1 and S2 sits inside A2. And this, of course, would imply the above result if we replace the square root of n over p by little o of n, because if we have such a backbone, then for any two cuts to get from one to the other, we will at most have to move some vertices outside the union of S1 and S2, and outside of the union, we only have little o of n vertices. So kind of the goal of this talk and our main result is to prove that the answer to this question is affirmative, and we'll be able to find such a backbone typically in GNP. But in fact, and this will be very important for applications when as you will see later, we'll ask for a slightly stronger statement. So we don't want this property to hold for any cuts which are actually largest, but also for any cut, for a pair of cuts, or sorry, for the family of cuts which are nearly largest in the following sense. So this quantity here, the largest size of a cut minus the size of a given cut, I'll refer to it as the deficit of the cut. So max cuts are the cuts of deficit 0. Cuts of deficit 1 are the ones that are at most 1 away from a max cut. And max cut with index d of G will be the family of all partitions which lead to a cut with small deficit, with deficit at most d. Now, here's a key definition which was introduced in the work of Bobby DeMarco and Jeff Kahn. We'll say that two vertices x and y are GD equivalent if x and y always appear on the same side of every cut of deficit at most d. So every cut of deficit most d will always put them on the same side, either both in A1 and both in A2. It's easy to see that this is an equivalence relation. It's clearly reflexive and symmetric, and also it's not difficult to check that it's transitive. And by EQ of D, I'll denote the set of all pairs of vertices in this relation. So this is an equivalence relation. So EQ of D is just a union of cliques, vertex disjoint cliques on the same vertex set as G. And also this notation int of pi, this means edges that are internal to pi. So given some partition, int of pi are the union of two cliques on the vertex set, which are the sides of the partition. And it's easy to see that the set of pairs that are equivalent is precisely the intersection of the edge sets of all these cliques. Because for every partition, the two cliques are pairs of vertices that do not cross this partition. And of course, to be equivalent, it means we cannot cross any of the partitions. So it will be the intersection of the edges of all those cliques. Is this okay? Okay. So let me recall again the definition. X is in relation with Y, which means that they are in the same part of every cut of deficit at most D. And this is an equivalence relation. So it partitions the vertex set of the graph into equivalence classes. And somehow a good scenario for us is that there are two equivalence classes, S1 and S2. The two largest ones each of them has more than a third of the vertices. If each of them has more than a third of the vertices, it means that every other class needs to have fewer than third of the vertices. And therefore, S1 and S2 are uniquely determined, and we'll call them the D-core of the graph. So if we have two large equivalence relations, it means that these two sets of vertices are respected by every cut of deficit most D, and we will call it the D-core of the graph. Here's our main theorem. Maybe first, before I get to the parameters, it basically says that the probability that G and P does not have a D-core is small. And let's read into the parameters. So we're able to prove it for kind of every D and P between 1 over n and 1 minus epsilon. And there's also an additional parameter alpha. So the question of Brightwell, Panagiotou, and Steger asked about the core, about a zero core, so that both the sets S1 and S2 had size n½ minus little o of n. So we allow to parameterize it by alpha. So alpha is the fraction, more or less the fraction of vertices that are left outside of the union of these two sets that form the core. And our result allows to take alpha to be even polynomially small in NP, 1 over NP to a quarter. And we get some explicit estimate on the probability. So kind of the main term is 1 over square root of NP. And if 1 over square root of NP tends to 0 quickly, then this allows us to increase D, so deal with cuts with some deficit, and decrease alpha, so get a core which really fills not only n minus little o of n vertices, but we're able to make this little o of n explicit by taking some explicit function alpha. And some comments about this estimate. If alpha is just a very small constant, so this is exactly kind of the question of Brightwell, Panagiotou, and Steger, we just want the core to cover all but little o of n vertices, then the upper bound here on the probability is roughly D over square root of NP, which means that we can consider cuts with deficit almost as large as square root of NP. Now, why is this interesting? I wrote here that this is optimal because in a typical maximum cut in GNP, most vertices will have only square root of NP vertices, neighbors more on the opposite side than on their own side. So if I consider cuts with deficit 1,000,000 times square root of NP, then I take a max cut and almost every vertex I can move to the other side, losing, say, 10 square root of NP vertices. And this way, I shatter all the max cuts, because if I am able to move this vertex from one side to the other, it means that it doesn't share the same side of a cut with any other vertex. Not on its own side, and not on the other side. So some constant times square root of NP is an absolute bound on for what deficit can we expect to have this core property. And we also need some lower bound on alpha, and kind of this comes from a failure of the union bound argument. A union bound argument cannot rule out a max cut which is slightly unbalanced, where this unbalanced is 1 over a fourth root of NP. So slightly unbalanced cuts have slightly fewer edges going across, but we cannot rule it out. If kind of the deficit in the complete graph is not large enough, a union bound argument cannot rule out that actually one of these cuts, even though it's kind of less likely, the expectation is slightly smaller, but perhaps by chance it actually becomes the max cut. And kind of one thing that, and this relates to Jihan's question, in fact, we are not able to show that with probability omega of 1, GNP doesn't have a unique max cut, which is, I strongly believe that this is true with probability actually 1 minus little of 1, but we just don't know how to show that typically in GNP you have more than 1 max cut. Questions about the statement?
So Wojtek, so heuristic, why more than 1 max cut? Because, right, you kind of should jump occasionally, right?
Right. So here's the heuristic why there should be more than 1 max cut. Suppose that there's always only a unique max cut. So in order to increase the size of the max cut, so consider the random graph process, add edges 1 by 1. The next edge comes, when does it increase the size of the max cut? Only if it crosses some max cut. And if the max cut is unique, then it means you have to kind of all the time cross this cut. But this cut has slightly more than half of the edges by this error term. So you actually, the next edge which comes randomly is slightly less likely than 1/2 to cross the max cut. So on the one hand, you expect kind of the growth of the max cut to be slightly less than 1/2, but you know that in reality, the max cut grows slightly faster than 1/2. And this is a contradiction. So kind of in this expectation sense, the max cut is not unique, but we cannot turn it into any argument that gives it with probability, which is bounded away from 0. So we know that it's probably at least 1 over square root of NP or something like that, but we don't know that this is actually the typical behavior. Thanks, Benny. It's a very nice question.
Wojtek, why did you say that if you consider the random graph process, this edge is slightly less likely to be in the...
So suppose now I considered random graph process, meaning the graph G and M, and suppose that G and M is, so first of all, if I fix G and M, then the next edge that takes it to G and M plus 1 is just a random non-edge.
Yes.
But if G and M has a unique max cut, so say this is the cut, and note that this cut has slightly more than
right. That's true.
And here slightly less. So you're slightly more likely to for the new edge to come as a non-crossing edge than a crossing edge.
Yes. And what is the other side that you gave a contradiction heuristically?
Heuristic, because we know, from the previous slide that actually the max cut is slightly more than 1/2. This probability that the new edge crosses, it should be slightly above 1/2 by some kind of polynomially small factor, but still slightly above 1/2.
Okay, you meant that. Okay, yeah. Thank you.
Okay, so now how did we get to this problem? Actually, we got to this problem motivated by 2 questions or 2 problems posed by the work of DeMarco and Kahn. So kind of they were studying the following question. You all know Mantel's theorem, which says that the largest triangle-free subgraph of Kn is the complete bipartite graph. And people have been interested in the following question: what can you say about the largest triangle-free subgraph of G and P? What do you need to assume about P to make sure that even actually in G and P, the largest triangle-free graph is equal to its largest cut? And what DeMarco and Kahn proved is that this function, square root of log n over n, is a threshold function for this property to hold in G and P. So above some large constant times this function, indeed, the largest triangle-free subgraph of G and P is equal to its largest cut. In a recent work with Ilay that actually I realized today I spoke about it in this seminar some year ago or 2 years ago, we proved the statement with some explicit constant here. It was square root of 3. And Jeff and Bobby had some prediction for what this constant should be, and their prediction didn't agree with our prediction. And so we kind of developed this whole machinery to be able to show the respective zero statement. So one of the corollaries is that if you're slightly below the square root of 3, then in fact, for every max cut, A1, A2, and G and P, you will typically find an edge, UV, that is internal, that you will be able to add without creating a triangle. So there is some edge in G and P, which doesn't close any triangle with the edges going across some max cut. So you can add this edge. The graph is clearly not bipartite because we added an edge, internal edge to a max cut, but it's still triangle-free because there's no closing triangle. And the second corollary, which was also a conjecture of DeMarco and Kahn, says that typically in G and P, if you look at any max cut, then every vertex will have more or less the same number of neighbors on both sides of the cut. So the argument that you know from graph theory is that every vertex in any graph has at least as many neighbors on the other side of every max cut on its own. And what DeMarco and Kahn conjectured is that, in fact, in a random graph, no vertex has significantly many neighbors on the other side and its own side. And this is what we managed to prove under the assumption that P is asymptotically greater than log n squared over n. They conjectured log n over n. So we're missing this logarithmic factor, which I think would be kind of interesting to close, but our methods do not allow it. And in the remainder of the talk, I want to sketch the proof of the theorem, just in the case D equals 0, so max cuts, and also give a kind of really sketchy proof of corollary 1. So how does this theorem allow one to prove statements of this form? And the biggest challenge, of course, is a potentially enormous union bound over max cuts, because for a fixed cut, say, this holds only with polynomially good probability, and potential union over all max cuts would be exponentially large, and kind of this notion of stability of cuts allows us to really overcome this potentially massive union bound. Okay, so any questions about the statements of these corollaries? Okay, so let me move on to the sketch of the proof.
For the first corollary, I have a simple question.
Sure. Mm-hmm.
Do you think the neighborhood could be extended to distance neighborhood also? Or I only said
I see. So if for a very sparse graph, you would like to kind of study the number of vertices of distance 2 and so on.
Yeah. Do you think could be? Because I read your paper on the internet.
I believe yes. I believe yes.
Yeah.
Somehow
so I think could move on to the distance neighborhood because you divide them.
Yes,
equally.
I believe the answer is yes.
But
I believe the answer
probability
is perhaps at the price of increasing this log power here.
Yeah, you should
Very
maybe the
slightly.
larger or more larger or the distance, the probability could be the same condition. You
It
think?
could be this. Perhaps you would need to sacrifice another log power. But
Thank you.
yeah, likely such a result would be true.
Well, I think it is
With kind of
it's
similar proofs
totally.
too.
Thank you. Go on.
Okay, so now let me say a few words about the proof, kind of just in the case d equals 0, which is somewhat easier and kind of the also it's clear from the proof why the theorem is true. So just recall, because we'll be heavily using the notation here, b of g was the largest size of a cut. And EQ of G, where I remove now this index 0 because we're only dealing with case D equals 0, these are all pairs of vertices which are always on the same side of every maximum cut. So the EQ stands for equivalent. And our goal is to prove that with this condition on P, so P is greater than 1 over n, but not very close to 1, typically in G and P, we will have two sets S1 and S2, both of size roughly half of all the vertices, with the property that every max cut of G and P, A1, A2, A1 contains S1 and A2 contains S2. So this is the backbone of all the max cuts in G and P. And I don't want to get into technicality, so I just took alpha to be little of 1, and instead of an explicit bound on the probability of failure, I just say that this holds with probability which is asymptotically 1. Now, it all really boils down to the following observation, which is true not just for a random graph, but actually for every graph. Consider a graph G and a pair of its vertices that is not an edge. And note that the following four statements are equivalent. The first is we add E to G. E is not an edge of G. We add it to G, and this increases a max cut, the size of a max cut. When can it happen? Of course, it means that E has to cross some max cut, because otherwise we wouldn't be able to increase its size. It crosses some max cut is precisely the same statement as saying that E is not, the endpoints of E are not on the same side of every max cut, because for some max cut, they need to be on different sides. And this means in our notation that E is not one of these equivalent pairs. And finally, if we added E to G and increased the size of a max cut, of course, now E has to cross all the max cuts of this larger graph, because otherwise removing E wouldn't reduce the size of a max cut, but the first condition is that it does. So how does it help us to prove the statement? So here's the setup for the proof. We'll consider the random graph process, but just one step of it. So G1 will be a graph, uniformly chosen graph with n vertices and m edges. E will be a uniformly random non-edge of G1, and G2 will be the union of G1 and the edge E. So of course, we took a G and M, we added a random non-edge. This means that we get the next graph in the random graph process. And also note that the last edge that we added E is also a uniformly random edge of G2. Now, let's look at the following quantity Q. It's the probability that E is not an equivalent pair for G1, so that it crosses some max cut of G1. And by our observation, this is equal to the probability that E crosses all max cuts of G2, because crosses some max cut of G and crosses some all max cuts of G union E were equivalent statements. Note that the probability that E crosses all max cuts of G2 is no more than the probability that E crosses some canonically chosen max cut. And what is the probability of crossing some canonically chosen max cut? Well, it's the number of edges in this max cut divided by n plus 1 because E is a uniformly random edge of G2. And then this expectation averages over the choice of G2. Now, but we know now that B of G2 is roughly half the edges with extremely high probability. So this expectation is easy to bound by a half plus little of 1. So if when we use the union bound argument to give an upper bound of B of G2, actually the probability of failure is exponentially small in n. So we easily get this 1/2 plus little of 1. Now, on the other hand, and for simplicity, I'll denote n choose 2 by capital N, what is 1 minus q? 1 minus q is the probability that our randomly chosen non-edge of G falls into this set of equivalent pairs. We had n minus m choices for the edge because G1 has m edges and Kn has n choose 2 edges. And when does it fall into EQ of G1? Well, we have EQ over G1 options, but since we're only choosing non-edges, we have to subtract the intersection of EQ of G1 and G1, and then E again averages over the choice of G1. So 1 minus Q, we have this following explicit expression for it. Now, whenever you see an expression like this, when you study concentration, you should be immediately suspicious because I'm trying to say something about the intersection of the edge set of G1 with some set of pairs which depends on G1. So I would love to write here that this is, the density of G1 times the size, but I need to give some argument because maybe I could take G1 intersecting the complement of the edge set of G1 and the intersection would be 0. But what do we know about G1? So about EQ of G1. EQ of G1 is the set of pairs in an equivalence relation that is determined by G1. So in particular, we know that it has a fairly simple structure. It's a union of cliques, vertex disjoint cliques in the complete graph. Now, there aren't too many such graphs of this form, only about n to the n. And therefore, it's enough to guarantee, in order to guarantee that this is close to the expectation, will require of G1 something stronger, that it will intersect any union of vertex disjoint cliques in its expectation. And this kind of one can show that the probability that this intersection exceeds its expectation, undershoots its expectation by little of m, is already exponentially small in n. And we really use the fact that EQ of G1 has a simple structure. Now, using this fact and combining 1 and 2, we get that 1 minus q is at most 1 over n times the expected size of EQ of G1 plus some error term, which is little o of mn. And combining our upper bound on q with our upper bound on 1 minus q, we get a lower bound on this expectation. So in expectation, the number of equivalent pairs in G1 is at least half of n choose 2. And this already looks pretty good. For the following reason, sorry, so maybe let me give some intuition. If we know that EQ of G1 is a union of cliques, and we know that the total number of edges in this cliques is roughly half of the edges in Kn. So if we knew that none of these cliques is larger than half the vertices, then this immediately implies that the two largest ones have to have n over 2 vertices each. Otherwise, we wouldn't be able to acquire half the pairs. So now, in order to complete the proof, we just need to show that in a typical max cut, none of the parts has size significantly more than a half, and therefore, also in EQ of G1, these cliques have to be subsets of the parts in any cut. So this would be also true about the class sizes in this equivalence relation. And kind of this is pretty straightforward, just from standard concentration. If if a partition is unbalanced, then you expect significantly fewer than half the edges to cross, and therefore you will never be able to catch up with the max cut. So in particular, we know that every clique in EQ of G1 has at most roughly half of the n vertices. This means that twice the equivalence number in G1 is at most, for every vertex out of n, it has at most 1/2 times n vertices that are equivalent to it, because every equivalence class has size 1/2 n, and this sums up to n choose 2. And kind of the proof of this is just union bound and standard tail estimates. So what's the conclusion? On the one hand, we know that the expected size of EQ is half n choose 2, but we also know with very, very high probability, EQ is at most half times n choose 2. So this means that with probability 1 minus little of 1, EQ is about half n choose 2. And since EQ is about half n choose 2, and it's a union of cliques, none of which is more than n over 2, it must be that there are two cliques of size roughly n over 2. And these two cliques means two equivalence relation in our two equivalence classes in our equivalence relation are of size n over 2. So there are two sets of vertices of size n over 2 each, so that the vertices in each part behave the same with respect to every max cut. And this is precisely the backbone for all max cuts that we were interested to find. Okay, questions about the proof?
So, Wojtek, can you again repeat this? Why the fact that it's a union of cliques?
Sure, because suppose now, okay, this is a great question, Benny. Let me kind of sketch some.
Yeah, this number
how
3.
How many unions of cliques do you have? Well, at most n to the n. So you have the union size of the union bound is n to the n, and again the probability that a binomial random variable exceeds its so the expectation here is m because it's g and m. So now the probability that g and m intersection some union of cliques has size bigger than smaller than expectation minus some epsilon m. This will be at most exponentially small in minus epsilon squared m squared divided by the expectation, which is no more than m. So here you get something, which is already exponentially small in m, but the union bound is only n to the n. So this still would, the way I wrote it would require m to be at least n log n, but then you notice kind of extra things that, most of these unions of cliques that are counted here have cliques that are very, very small, and therefore you're not dividing here by m, but you're dividing actually by the expectation, which is significantly smaller than m, and this allows you to get rid of this log factor. Okay, great question, Benny. Okay, I have about 10 minutes left, and yeah, so I promise that I will finish way ahead of time, and of course, I have a reality check now. In the last 5 minutes, I just want to indicate how this statement about kind of stability of max cuts allows one to prove some statements about the behavior of kind of edge distribution with respect to all max cuts. And the statement about triangles in GNP kind of is significantly more difficult to prove. So let me kind of focus on corollary number 1, which has simple statement, and kind of the ideas behind the proof are kind of much more explicit. So I want to prove the following statement. Typically in GNP, every vertex has roughly the same number of neighbors on both sides of every max cut. And here's a key observation. Suppose I have two graphs on the same vertex set, and suppose that G has some D plus ET core. ET is the number of edges in T, S1 prime and S2 prime. And suppose I modify G by taking its symmetric difference with the graph T. So a small modification of G. And I claim that this graph now has a D core. So this graph has two sets which are respected by every cut with deficit at most D plus ET. This implies that the slightly perturbed graph still has a core which is respected by now every cut with deficit at most D. And the reason for it is that modifying the graph by changing at most T adjacencies will not change the deficit of any cut by more than the number of edges that we perturb the graph by. So let me kind of not get into the proof, but this is kind of an easy statement. We perturb graph very little, which means that the deficit of all cuts cannot change by more than the number of edges we perturbed, which means now that cuts that have deficit D before had deficit at most E over T, D plus ET, but we knew well how to control graphs, cuts with deficit D plus ET, which means that we can control well the graphs with deficit at most.
But then you need to write the T small perturbation, right? Because you didn't say it anywhere.
So ET is just the number of edges of T.
Okay. Yes.
And then moreover, not only it has a core, but the nice thing is that the new core contains the old core. Okay, so here's here's the setup. We take D to be logarithmic in N, and we take G to be, we condition G and P on having 2D core, which also means we have a zero core, and we call the zero core S1, S2. Now, let me R be a uniformly chosen D subset of the neighborhood of V. I fix some V. And we modify now G as follows. We take G and we resample the edges between V and this random set of its neighbors. So we don't change more than D adjacencies. Now, by our observation, since G had a 2D core, G prime has a D core, but also G is a modification of G prime, which means that the D core of G prime is contained in the zero core of G. And the key lemma is that, so we take G and we resample R and let G prime be the new graph. Since we resample the edges of R, and when we look at G prime, then R is very close to a uniform subset of the vertices other than V, because we resample. So this is a calculation that one needs to make, but kind of the intuition is, since we took G, resampled something, and then we got G prime, to know which edges were resampled, we have no clue. So it's essentially a random subset of vertices outside. And here's the punchline. The following two things happen with probability, which is polynomially small. First, since Si prime, which depends only on G prime, this set has size, since the set R from the point of view of G prime is a random subset of all the vertices, then it means that it will intersect Si prime roughly in half, because Si prime is roughly half of the vertices. In similar manner, since R is a random set of neighbors of V, then it will intersect Si in the same proportion as the neighborhood of V intersects Si. So degree in Si divided by the degree. And kind of this is the quantity we're interested in studying. We want to say which proportion of the vertices, the neighbors of V, intersect Si divided by NP. And finally, Si prime is contained in Si, which means that this number is at most this number, and this gives us a lower bound on the degree of V in Si for every I. So for every I, we know that the number of neighbors of V in Si is at least half, which means that for every max cut, we have at least half of the neighbors on the other side, half of the neighbors on our own side. But of course, we have at most NP neighbors in total. So it also means that we can't have more than half in any of the parts. Yeah, I'm sorry this was a bit quicker than I expected, but let me stop here, and I'll be happy to answer any questions that you might have.
So thank you, Wojtek, for very nice talk. Yes, question, right? So maybe applause. Maybe you can do it with a hand here. Emojis, right? And then questions. Maybe I'll have a question. So when you now want to, so maybe just briefly, like a direction, want to prove from here that, you know, largest triangle free and bipartite graphs are the same. So what you should do
is basically, you know, this scheme of proof allows you to consider kind of, you know, most of the partition for every max cut. You can treat it as a fixed set. Kind of this is the punchline, because here we wanted to know something about the distribution of kind of small portion of the neighborhood of a vertex. And we resampled. And now in this graph G prime, this is just a totally random set. Because S1 and S2 prime are already determined by G prime. But S1 and S2 prime are very good approximations for the original core.
That part I understand very well. So you control max cut extremely well. You understand how it looks. But the triangle free graph you don't know anything about. Right?
But I just, you know, I want to prove something, of course, much weaker. I don't prove this, I just prove the zero statements. I want to show that typically I will have an edge so that I'm able to add it and not close a triangle.
I see. Oh, and
so I say, okay, I have this
once you understand, that's cheap. Okay. So it's not that you're telling us that this hard statement of with Ilay.
No. This is much more difficult.
Yeah. So that's what. Yeah. So this I understand. So once you know your cut, right, you basically see the place where to add this edge, and then.
Yes.
Okay. So this is what I missed. Okay. Sorry. Okay. More questions?
Wojtek, a very nice talk. You promised before, I think, similar things maybe also work for a tripartite cut or something.
Yes. So you see, if you look at the proof or the sketch proof, I didn't use explicitly the assumption that R is equal to 2, you know, other than this. So instead of B, I will write, you know, instead of B2, I will write BR, and this won't be 1/2, but this will be R minus 1 over R. And the proof, just, you can rewrite it.
So basically similar conclusions work for all the fixed.
Yes. For all R fixed, we have some explicit dependence in the probability bound on R, so you can also take R going to infinity at some small rate.
Maxed cut problem is a very traditional problem, but you can show something new. You can find the backbone for the maximum cut. I feel this topic is very interesting. I like a simple problem. My question is, you in your proof you use the uniform model hypergraph, uniform model GNM. I remember, and you. But the hypergraph model, I think could you know some results on the
Yeah, so
hypergraph
actually,
model?
we're working on it right now. There's a major technical obstacle here that for certain types of hypergraphs, in hypergraph, you have lots of different types of cuts, even in uniform hypergraphs. The cut could be like 1, 1, 1. You split into 3 parts and you're interested in triangles that are crossing, or you split into 2 parts and you want 2 1 edges and 1 2 edges. And for certain types of the cuts,
Linear hypergraph model, could you maybe think?
Yeah, kind of the issue is that for certain types of cut, the structure of these pairs that are always in the same side of the cut is no longer so simple. So this union bound now becomes really, really large. And we can prove something, but with non-optimal deficit. So it's the same proof scheme and the intuitions are clear, but this thing which I marked here with the red frame, this is really a kind of a making or breaking point of the proof.
I know uniform hypergraph is difficult. Thank you. But
Yes.
weighted version, for the weighted, I know max cut, weighted version for the max cut is very popular problem. But you could weighted have some weights. Could you extend to weighted version?
Weighted graphs. I
Weighted.
believe for kind of some sensible models of random weighted graphs, yes.
Okay. Thank you for your talk. Thank you.
So Wojtek, just to follow on this question, so when you're looking on hypergraphs, you still your equivalence class is union of cliques, but then it's much harder to kind of but much more.
But sorry, maybe for the 2 1 cuts, yes, but for the 1 1 1 cuts,
I see.
So the problem is that if you look at kind of the union, you have many different 1 1 1 cuts, and you want to look at the union of all the triples that cross some max cut. And this no longer has a nice structure.
I see. So you're losing. I see.
Because you partition into 3, and kind of these guys are not always in the same, and these two are not always in the same, but that doesn't mean that the triangle crosses.
Right.
So this is the difficulty.
So Wojtek, maybe one more question. You said that you can deal with the case where R is bigger, and I assume that maybe you can also say something about the case where you have K4-free subgraphs of random graphs, as opposed to just triangle-free subgraphs of random graphs.
Yes,
so
yes.
To prove 0 statements in the corresponding range.
Yes.
What the constant should be.
This also, sorry, this corollary actually. There's a version of it we can prove sharp constant for every clique and actually every strictly 2-balanced edge critical graph. And once you have the right proof for the triangle, then kind of the same proof works for every strictly 2-balanced edge critical graph.
And you're also getting 0 statement, right?
So the 1 statement we got with Ilay and the 0 statement, we can now match it using kind of this machinery.
And so what's the constant for KR? Is it square root R or?
This constant is, it's kind of a calculation. You just perform the calculation for a fixed cut. This will give you a prediction exactly for this property that you can add an edge for free. And this will give you some, bound on P, and you can kind of translate it now into a rigorous proof.
Okay, thanks.
Okay. More questions?
Wojtek, the other question is it possible to, for example, for the second statement here, can you say anything about the difference between the max triangle free graph and the max cut?
Right, very good question. There is a work of Will Perkins, Aditya Potukuchi, and Matt Jensen, if I remember well, who study very similar questions. So instead of largest triangle-free graph in GNP, they study a typical triangle-free graph with M edges. And these two problems, even though I fail to see any kind of formal connection between the two, but phenomenology is exactly the same, and they are able to say something. There's some threshold above which a random triangle-free graph with M edges is bipartite, and they're able to kind of study the structure of the graph below the threshold. How many edges do not cross a max cut?
That's cool.
If you send me an email, I'll send you a reference.
Okay, thank you.
More questions? So if not, let's thank Wojtek again.
Thanks, Benny.
Bravely answer all our questions, right? And very in very precise manner. So we can stop the recording.